Hi, all, Mr. Lim here. No, so this one here, draw the line and then draw the displacement line different. Okay, so the displacement line is there. The distance is the total distance, 7 plus 6 plus 2, which was 15, and the displacement was in the northeast direction as the green line. You can work that out by Pythagoras. 5 squared plus 6 squared is equal to c squared. C is equal to the square root of that total, which makes that 7.81, right? And then this one here, scalar has direction, but no magnitude. Has magnitude but no direction, and then the 20 meters is that, and then the vector has direction and magnitude. All right, so this one here, dingo tracked, right? C to D, what is the speed? Speed is equal to distance over time. What is that then? How far has it gone? All right, it's gone 200 meters only. So it's gone from 100 to 200 meters between C and D, right? So the distance is 100. What is the time? It's taken from 30 seconds to 60 seconds here, 30 seconds to 60 seconds, which happens to be then 30 seconds, right? So 100 divided by 30 is some value. What's that going to be? Like 3.33 meters per second, something like that? No? What's that value? Okay. 3.3, okay, yeah, that's what I thought. Yeah, see, 3.3 meters per second, right? Do I need to put the direction? No, because it's asking for speed. Describe the motion of the dingo between D and E. What is it doing here? What is it doing there? It's being stationary because it's a flat line on a distance time graph, so therefore it is stationary. Oops, that's not what I wanted. Stationary. Right? State the 10-second time period using the grid where the dingo is moving the fastest. Explain how you came to that answer. So looking here, what are we looking for when we are looking for the fastest part, Jisnu? The steepest curve. Where is the steepest curve? It's round about here. The 10-second time frame where it's the steepest curve is there. So it's between 100 and 110 seconds. All right. You'll notice that this entire area between E and F is accelerating, right? And so therefore, it's just getting faster and faster. And so therefore, it's accelerating the fastest, or it's moving the fastest at 100 to 110 seconds. Right? Next. Student is traveling on an electric scooter in their driveway. If they travel 15 meters in 6 seconds, what is their speed? Okay, so speed is equal to the distance over the time, which happens to be 15 over 6, which happens to be some value. I don't know what that is. What's like 2.5 meters per second. Please remember that. Also, please remember that there are different ways to show meters per second. That's one way to show meters per second. That's another way to show meters per second. All right? So there are different ways to show meters per second. If they move at 2 meters per second for 7 seconds, how far will they move? So that's distance is equal to speed times time, which is equal to speed 2 times 7, 14 meters. Right? So this one here. So please note that when you have these calculations, you are going to have to take note of the units, all right? If it's in meters, or if it's in kilometers, or if it's in hours, or minutes, or seconds. So you will have to be able to convert between hours, minutes, and seconds, and between meters and kilometers. If you have trouble with that, please let me know, and I can come and help you, all right? So how long will it take them to travel 45 meters at an average speed of 3 meters per second? Okay, so that's a time is equal to distance over speed, which is equal to 45 divided by 3, which is equal to 15 seconds. Right? You really should show your working as well if you want to get full marks. Right? If they accelerate at 2 meters per second from rest for 4 seconds, how fast will they be going? So please remember that you can also have meters per second squared like that as a unit, but this is acceleration is equal to v, well, let's call that final, take away initial over time. However, we are looking for the final speed. The final speed is equal to the initial speed plus the acceleration times the time, right? So the initial speed is 0 plus the acceleration 2 times 4, which is equal to 8 meters per second, right? So that one there. How long will it take them to decelerate from 14 meters per second if they can decelerate at a rate of 5.7 meters per second, right? So how long? That's again a time. Time is equal to what? F take away I over A, right? 14, oh wait, yeah, 14 take away 0, right? That's in the wrong order, but that's okay, because we are just looking for the change in velocity, right? Divided by the acceleration, which is 5.7, and so therefore that will give you a value. What's that value? What did you get, Kalen? 2.46. Yeah? 2.46, close? Sorry? Yeah, 2.46 seconds, right? So you can all do that on a calculator, yes, so I'm just showing you how to do it. Student accelerates at 1.3 meters per second for 5 seconds and reaches a speed of 10 meters per second. How fast were they initially going? So this is asking for the initial speed, which is equal to final speed, take away acceleration times time, right? So the final speed is 10 seconds, 10 meters per second. The acceleration was 1.3 times 5. 1.3 times 5 is 6.5. So 10 take away 6.5, which is equal to 3.5 meters per second. Right? So you will need to remember those rearrangements of the acceleration equation. A is equal to final take away initial over time. Final is equal to initial plus acceleration times time. Initial is equal to final subtract acceleration times time, and time is equal to final take initial over acceleration. Right, and you'll be able to watch this on the video that I make at some point. Right, let's have a look at this one here. Draw the following journey. They move 120 meters east. So they're starting at 0. 120 meters is here, right? 60 seconds means that they end up there. So you should draw a straight line from there to there. They stay at their lock of 20 seconds, which is 60 to 80. And then they move 120 meters west in 120 seconds. So 120 seconds from 80 seconds is 200 seconds. So they need to end up here. And then they move 120 meters west, which means they move the opposite direction. So they end up here, back at their original starting point. And that's the graph that you should draw. What was their overall displacement? They've gone nowhere, because they ended up and started at their original place. Remember, displacement is beginning and end. What was their velocity? 0 meters per second, because they haven't gone anywhere. Right? Velocity is equal to displacement over time. So you need to make sure you remember that. Oh, but sorry, that was their velocity on the way to their locker. Should have done that. All right, so 120 over 60 is the initial one. Their velocity, which will be equal to 2 meters per second. Is that the final answer? No. I need a direction, which is east, I think. Right, what was their velocity on the way back to class? 120 divided by 120, which is equal to 1 meter per second. So just like you, they walk slowly back to class because they're lazy like you guys. Right, and there's your 1 meter per second west. What was their average speed? So they've moved 240 meters because they moved 120 forward and 120 back. And how long did they take? 200 seconds. So 240 divided by 200 is some value. What is that? Okay. What is that value? Some call it out, Matthew. 1.2 meters per second. Do you need a direction here? No, because it's a speed. Right, what was their average velocity? Their velocity is 0 over 200, which is 0 meters per second. Right, because they didn't go anywhere. Right, and then finally, I think this is the last one. All right, so drone being flown by students, what was their acceleration from 0 to 5 seconds? So acceleration is equal to final takeaway initial over time. So their final speed after 5 seconds is this value here. What's that value here? It is 6. All right, so you should see that there are 5 divisions between 0 and 10, and so therefore that's going to be a 6. So 6 take away 0 because they started at 0 over there, right? And the time taken was 5, so 6 over 5 is like 1.2 meters per second, right? Alternatively, I can write it as meters per second, like squared like that. However, that's not correct. What am I missing? A direction, which means that I need to say that it's going south. At which point in time was the object stationary? So remember, this is a velocity time graph. If it's a velocity time graph, it's stationary when it reaches the x-axis. So it's at 0 seconds and at 15 seconds. Right? What was this acceleration between 13 and 15 seconds? Okay, so acceleration, A is equal to final. So between 13 and 15 seconds is here, in this area here, right? 13 to 15 seconds, that's there. So his final velocity is 0. His initial velocity was 8. And the time was 2. So -8 divided by 2 is -4 meters per second squared. Whoops, that should be like that. Yeah. Right? And you can also write it like this, meters per second squared, like that. But that's not finished. What am I missing? I need a direction, right? So the direction, I could say it's a negative in the eastward direction. Alternatively, I could say it's 4 meters per second squared in the west direction. Okay? It is doing what in that period of time? Is it speeding up or slowing down? Matthew is paying a lot of attention and doing spitballs. So you're going to be cleaning up that spitball and anything else I find in this room. Pick it up now. Is it speeding up or slowing down in that time period? It is not speeding up. It is slowing down because it's getting closer to the x-axis from 13 to 15. Right? At what points in time was it moving south? All right? Remember that this is velocity in meters per second south. Right? Velocity per meters per second south, which means it's always moving south. Right? Even though it's slowing down at the end, it is still moving south. So between 0 and 15 seconds, which is all of the time it's moving south. It will only be moving north if it goes below the x-axis. Then what is the total displacement of the drone over the first 10 seconds? So you're trying to work out the area underneath the curve between in that area there, right? That entire area there. So there's a couple of ways that you can do this. I would separate out into this triangle here, this rectangle here, this little square here, and then this little triangle there. All right? You could work out the area, make sure you pay attention to the scales. All right? Half base times height for the first one, so that's 5 by 6. So I'll just write it over here. Right? 5 by 6 divided by 2, which is 15. 5 by 6, which is 30 for that green one. Right? 1 by 2, which is the yellow one, which is 2. And 4 by 2 divided by 2, which is equal to 4, which is that bit there. All right? So that as a total is what? 45, 49, 51. 51 meters. Right? Is that the final answer? Incorrect. It is 51 meters south. Okay. Hi all, it's Mr. Lim here again, and we are just going to go through this second part of this revision worksheet. So let's go through. So on the following grid, graph the motion described below. So we have to work out how to graph this one, okay? So we need to be able to graph this. We need to work out what type of graph it is. So looking at the information says that we need to start graphing things like 2 meters per second, 10 meters per second, 1 meters per second, right? So this is going to be a velocity time graph because it's asking us to graph some velocities, right? So if we're, first thing you need to do then is to write out the axes or the axis labels. So this is going to be velocity and this is going to be time. I'm just going to write it over here, right? The units for these is going to be meters per second because that's what we saw in the information. And the time is going to be in seconds, right? We're going to put a title on here, velocity time graph, right? Okay, then we need to work out how big we need to make this scale. So let's have a look. So let's look at the time scale first. We got 3, 5, 4, and 8 seconds. That makes 20 seconds, right? So we're going to go 20 seconds across. So we've got to make sure that our scale gets to 20, right? There are 5, 10, 15, 20 boxes. How convenient, right? So 0 to 20 and 10 in the middle, 15 over here, and 5 there. Okay, so what you should always do is you should look at your information, work out how big you need to make your graph, and then, then you work out your scale, right? So the object initially started at 2 meters per second, then it accelerates to 10 meters per second, then it accelerates further, so it needs to be greater than 10 meters per second. So let's have a look. I got 20 boxes up. Okay, so I think I got 20 boxes up, 5, 10, 15, and 20. Okay, so if we do ones over here, that's also going to be good. 10, 15, and 20. All right, because this is a velocity time graph, I'm missing one piece of information. I'm missing the direction on the velocity. It seems that all of these things are going east, so we'll just use velocity east. Okay, cool. So let's have a look at the thing. So the information starts off with the object initially started at 2 meters per second east for 3 seconds, which means for 3 seconds, it's going at 2 meters per second. So for 3 seconds, which is up to this point there, okay, so that's on this line here, it's going at 2 meters per second, which is this line here, right, for 3 seconds. So it's going to be going at 2 meters per second for 3 seconds, which is that line there, right? Then it accelerates to 10 meters per second over the next 5 seconds. So it accelerates to 10 meters per second. It accelerates to 10 meters per second over here over the next 5 seconds. So 1, 2, 3, 4, 5 seconds will be 8 seconds. Okay, so at 8 seconds, it's going to reach 10 meters per second, which means that I need to put a dot there. Okay, so I put a dot there. 8, 10, there it is, right? And it's going to have a line between there and there, and you should use a ruler to do that, right? So it then accelerated at 1 meter per second over the next 4 seconds. So it's accelerating at 1 meter per second. So in the first second, it's going to be 1 meter per second faster. In the next second, it's going to be 1 meter per second faster. In the next second, it's going to be 1 meter per second faster. And in the next second, it's going to be 1 meter per second faster. All right, so that's this one here. Okay, it looks like it is the same gradient as the last line, but it's not. Okay, so you have to just be really aware of those things. And then it decelerated to rest over the next 8 seconds. So rest means it goes to 0, and 8 seconds later, 1, 2, 3, 4, 5, 6, 7, 8 means it hits 20 seconds. Right, so goes to rest It's at the bottom 8 seconds later, which means you have to draw all the way down there. Okay, so that's that graph there. So what's the overall displacement of the object? Right, the displacement from a velocity time graph means you have to work out the area of this graph. Right, so we can divide that up into different sections. This section here, I'd say this section here, right? I'd say this section here. I'd say this section here, just one big triangle. Then there's a couple of rectangles, this rectangle here, and this rectangle here. Okay, so we'll just number these 1, 2, 3, 4, 5, and 6. Okay. All right, and that's how you would do it over here on the right. So you can go work out the area of each of those shapes there. So the overall displacement is the total of those values. So that's 6 plus 20 plus 10 plus 40 plus 8 plus 56. Okay, that makes it 140 meters. Okay, and what's that? It's a deceleration at 18 seconds. Okay, so deceleration is the change in velocity. So at 18 seconds, which is over here, it's decelerating at a constant rate, which is from here all the way to there. So if it's decelerating at a constant rate, we can just go work out its deceleration over that entire time, right? So acceleration or deceleration is equal to final take initial over time. Okay, so that is its final velocity is 0. Take away its initial velocity, 14, over the time that it takes, which is 8 seconds, which is 14 divided by 8, negative 1.75 meters per second squared. All right, now it's negative because we're slowing down, but its acceleration then could also be described as west. So you can say that it is negative 0.175 meters per second east. Alternatively, you can say 1.75 meters per second squared west, because it's accelerating in the opposite direction by decelerating. All right, let's have a look at the next question. Okay, so for the following velocity time graphs, answer the following questions. We want the initial acceleration of both lines. So the initial acceleration, again, is just talking about what is the rate of change of that line and the rate of change of that line. Okay, and that's the initial parts there. So the acceleration is equal to final take away initial over time. And for the red one, it's going to be the final velocity is, each of these is 0.6. So this is 3.6, 4.2, 4.8, 5.4. Okay, so you do have to just work out that scale. Right, so the final velocity is 5.4, subtract the initial velocity, which is 0. And then the time that it takes was, these are each 2 seconds, each box is 2 seconds, whoops. So therefore, it took 4 seconds to do so, right? And so that red one is 5.4 divided by 4, and that's 1.35 meters per second squared, right? But I've got to look at the direction, so I've got to say it's north. And then the blue one is going to be, goes from 3 to 0, that's its change in velocity, over how long? So that's 12, 14, 16 seconds. So 3 divided by 16, which is 0.188 meters per second squared. That's also north, right? List the points in time when both lines show no acceleration. So when does it show no acceleration? When it is flat. Okay, so there's no change in velocity. So it's there. Oops, that's not what I wanted. Right, so there's one time here, one time here, and one time here. But what it's saying is that list the points in time where both lines show no acceleration. So the only times where it's showing no acceleration for both lines is between here and here. Right? So therefore, the answer would be then between 18 and 24 seconds. And list the points in time when the object was heading south. So this is velocity north. So you've got to remember that it will only head south if it is below the x-axis, because everything above that x-axis means that it's traveling north. Remember that if it's going down towards the x-axis, it's just slowing down. It's not necessarily going in the opposite direction. That's a displacement time graph. Right, so this one here, it's never heading south. Right, let's move on. This one here shows a path taken by a robot. I probably should have put a start and a finish. So there's the start, there's the finish. Right, determine the overall displacement of the object. Assume each square on the diagram is equal to a 1 meter square. So what it's saying is that what's its displacement, which is it's a straight line distance from start to finish. Right, so that straight line there, which can be solved as a triangle with a height of 3 and a length of a lot. How many is that? 5, 10, 15, 17. So a length of 17. So the overall displacement of this will be 17 squared plus 3 squared is equal to c squared. Okay, so this is Pythagoras. So 17 squared is 289 plus 9 is equal to 298. Okay, and so c is equal to the square root of 298, which happens to be 17 and a bit. 17.26 meters. Now, it is not enough to write that. I also need to write the direction. We're going to assume it's going north, south, east, west. So therefore, it is going in the southeast direction. Right. So, is the distance traveled of a total displacement of the robot larger? Okay, it is the distance. Why? Because the displacement is overall change in position, regardless of where it went before. All right, so you can see here that the robot traveled quite a bit before it reached the final destination. Right, so therefore that distance line, which is this blue line here, distance versus displacement, is going to be much larger than the displacement. Okay, if the robot traveled the distance in 20 seconds, calculate the velocity of the robot. So it's asking for velocity, which means that I need to use displacement. Probably should have written it like that. Okay, so velocity is equal to displacement over time. What's its displacement? 17.26, right, meters southeast. And the time, 20 seconds. So that value divided by 20 is 0.86 meters per second southeast. All right, there's that one. Let's go on to the next one. Okay, so conversions, remember. So, kilometers per hour, where have we got? Kilometers per hour to meters per second is divide by 3.6. And then meters per second into kilometers per hour is times 3.6. And that'll be in the data sheet there for you. Okay, so you can fill this out. All right, so that's what you get there for that table. All right, let's move on. Okay, so distance time graph. So remember, you've always got to identify what type of graph it is. What's the distance time graph? So what's the speed of the object between 0 and 10 seconds? So we are looking for the gradient at this point here. So speed is distance over time. Okay, so how far did it go? It went 25 meters in 10 seconds, which is 2.5 meters per second. All right, what is the average speed between 0 and 30 seconds? Okay, so this is a bit of a tricky one. So because this is average speed, it's asking for the speed that it's gone between 0 and 30. So effectively, how long if it went that far? So the question is effectively, how far did it go in 30 seconds? So in 30 seconds, it's up to here, and it's only traveled 25 meters. So the speed, it's traveled 25 meters in 30 seconds, right? So 25 divided by 30 is 0.83 meters per second, right? And so it's taking an average of the time that it stayed still, which is this point here, and the time that it was moving, right? So that's the average speed of the object between 0 and 30. And then what's the object overall displacement between 0 and 50 seconds? So this is displacement on a distance time graph. So therefore, effectively, it started here at 0 and it ended here at 0 at 50. So therefore, its overall displacement is 0 meters because it effectively went back to its original starting point. Okay, so it hasn't gone anywhere. And describe the motion between 35 and 50 seconds. So between 35, which is here, and 50 seconds, which is here. Okay, so it went like that, then it went like that. So it moved forward, I would say. Moved forward. Then moved backwards. And I would say that they occurred both at constant speed. Constant speed. And you could work out what that is, but it's just not asking you to, so we won't. Right. Then finally, let's do this one here. A motion tracking device is attached to a soccer player. As they move around the field and collects following information. Player moves 40 meters in 6.2 seconds. What's the average speed? So speed is equal to distance over time. So it's equal to 40 over 6.2, which is equal to some value. 6.45 meters per second, right? Player moves at 4.3 meters per second for 12 seconds. How far did he travel? So that's distance is equal to speed times time, which is equal to 4.3 times 12, which is equal to some value. Right, so that's 51.6 meters. Okay, how long will it take the player to run 150 meters of air running at 9.2 meters per second? So that is a time, which is equal to distance divided by speed. So therefore, they're running at 150 meters and they're running at 9.2 meters per second. So it would be some value, 16 and a bit seconds. Right. If a player slows down from 9.1 meters per second to 3.4 meters per second in 1.2 seconds, what is his acceleration? Okay, so we're doing acceleration now. So A is equal to F take I over T. Okay, so final 3.4, initial 9.1, time 1.2. And if you hadn't worked this out, this is going to be a negative value because he is decelerating, which is perfectly fine. Negative 4.75 meters per second squared. And because I've given it a negative, I don't need to give it a direction. Plus, I wasn't given a direction in the first place. Right. If the player kicks the ball from rest to 24 meters per second in 0.3 seconds, what is the ball's acceleration? So acceleration from rest to 24 meters per second. So 24 is the final, 0 is the initial, and the time is in 0.3 seconds. So 24 divided by 0.3, 80 meters per second squared. And we'll just say forward, because that's hopefully the way he's kicking it. And if the ball slows down at a rate of 1.4 meters per second squared for 6 seconds on the grass, what will its final speed be? Right, so this is the final speed. We're looking for the initial speed plus the acceleration times the time. Now, this is decelerating, So the initial speed is 24, but it's going to be slowing down at a rate of 1.4 meters per second squared, which means that it's a negative value for 6 seconds. So that's how we're going to show that it's slowing down. So 1.4 times 6 is negative 8.4. And if we subtract that from 24, we get 15.6 meters per second. Right, and that's its final speed after it slows down a bit. And that's all. Maybe there'll be another worksheet later on. Adios.